And I'll share my screen. If I ever do forget to do that step, please let me know. And I have our quiz open in a window right here. What we're going to do is actually type all of these things into the terminal, and we will see what the actual output is, going over why the output is what it is at each step. As we're going through these, feel free to ask any questions at any particular moment. Just shout it out or raise your hand. But also stop after each problem to see if there's any questions about anything. So in order to type these into the Lambda server, first thing is we have to log into the Lambda server. And so I have a terminal window open up here. And the way that I always get access to my SSH command again is the Control-R command to do the reverse search through my history. And if we just type in SSH, that gets me to the command right here. I'll have to actually switch this to our class account. There we go. Type in my password and we're logged in. And now we can run those commands. I'll put those on the same screen. And there we go. At the top up here, we have the quiz. And down here, I'll be typing in the commands. One command that we haven't gone over yet, which helps keep your terminal window a little bit organized, is the reset command, R-E-S-E-T, which will just delete everything in your terminal window, clear the screen, and move the cursor to the top like that. I'll be doing that in between each of these problems, just so that it's clear exactly when one problem starts and the next, or one stops and the next one starts. Again, for all of these problems, so we're starting with problem one. The first 4 lines of these problems are the same for all these problems. It just sort of initializes our quiz, make sure that there's no previous quiz folder here, puts us into this empty folder. And then that way, all the subsequent problems or all the commands will be independent of each other no matter what happened on the previous quiz problems. So we've just run these first 4 lines and we're on this touch readme line right here. Again, there are idempotent commands, which are good for debugging. Idempotent means it does not affect anything. And so one example of that is the ls command. I can always type that just to see what's going on. And here we have an empty folder. We just created that folder. And so the ls command prints out nothing to the output. And that's just good for us to know that we are in fact in an empty folder. I'm going to run the ls-a command as well right now. This is not the final answer right here because we still haven't actually done any of the quiz problems right here. I'm just running that to remind us what the -a flag does, that the -a stands for all. And so it's displaying all of the files. Every folder has these 2 dot files, we call them, inside of it. And they're dot files because they start with a dot. And by default, these dot files are hidden from us. So the ls command by itself doesn't display them. Okay, so we'll touch readme like that, run ls. The touch command creates a file if it doesn't already exist. So that created the readme file. And now we'll make this folder make dir foo like that and run touch foo/readme2 like this and touch readme3. The important things about this so far are, so we created this foo folder. This readme2 file is going to be put inside of the foo folder right here. But this readme3 file is not going to be put inside of the foo folder. In one of the practice problems, whichever one I copied this from, there was also a cd command in between these 2 things that would change our directory into the foo folder. But we are not running the cd command, so we are not running our, we're not changing the directory. We are not going into the foo folder. And so this will be created in our original quiz folder out here. This will not exist in the folder. This will, and this will. The final problem, or the final statement down here, ls-a, this will be the final answer right here, are these 5 files in the quiz folder. So readme3, readme, foo, ... and dot. In order to get credit on this problem, you have to have all 5 of those files listed. I don't care about the order of those things. But you have to have these 5 things listed, and you can't have anything additional listed. So for example, you could not have the readme2 listed down here. If you got all 5 of those things, you got full credit on the problem, 1 point. If you missed it in some way, then 0 points. Any questions about either the grading of the problem or why the problem gave us the answer it did? Okay, problem number 2. So again, first 4 commands the same: cd rm-rf quiz, make dir quiz, cd quiz, like that. And now we're on this 5th line right here with the make dir foo, like that. Echo hello space world into readme. Again, the greater than sign right here is output redirection. Before I run this real quick, so without output redirection, echo is another one of these idempotent commands. It does output to the screen, but it doesn't change anything on the file system. It doesn't change what files exist or don't exist. So if I were to run ls again right now, all we have is this foo folder right here created by the make dir foo command. Go back up, actually run the command from the quiz right here with the greater than sign readme. The greater than sign makes this not idempotent. It makes it actually change the contents of the folder, type ls. And so now that created this readme file with the output redirection. Let's do that again on the next line. Echo hola mundo into foo slash readme, like this. Again, this is going into the foo folder right here, not into this readme file, but into this other readme file. And I hit enter. Echo hello again into foo slash readme, like this. And this is going to be an important distinction for us at this point, that these 2 files are the same file. This file right here is a different file. These 2 files are the same file. And again, the single greater than sign, the single output redirection symbol, will overwrite whatever is the contents of this file. So when I run, I'm going to hit enter here in a second, and we'll run this. And when I do, it's going to delete this from the file, and only this will be in the file right here. I'll hit enter. We'll just verify that really quickly by running cat foo slash readme, and we can see that hello again is in the file, but hola mundo is not in the file. So we're on this echo statement right here at this point. We've done hello again, and now we're going to change our directory cd into foo, cd foo, like that. One more echo command, hola otra vez, like that. And now we have the double greater than sign. The double greater than sign appends to the end of the file, does not delete the contents of the file. And when we do the readme like this, even though this looks like a different different file potentially, because it doesn't have the foo slash in front of it, because we're in the foo folder right here, it is still in fact referring to the same file. And so we hit enter. The final command down here, cat readme, like this, hit enter, and we get both of the contents here, hello again and hola otra vez. Hello again from here, and the hola otra vez from this line right here. Again, the double greater than sign, meaning we don't delete the contents, we just append to the end. So that's why this is appended at the end. Yeah, as long as you have those 2 lines and not this, not anything else besides these lines as your output, then give yourself full credit. Otherwise, it's a 0 out of 1. Any questions on this problem? Yes.
Just in general, do you have to make the directory before you can make files inside a directory?
Good question. So here we were using output redirection and trying to before doing foo slash readme, I ran the make dir. Let's try this again. Hola mundo into bar slash readme, and you'll see that we get this no such file or directory because bar didn't exist. So yeah, with output redirection, at least in we're currently using what's called the bash shell. Later today, we'll be talking about different shells have different behaviors. Bash requires you to have these folders exist, and other shells don't require it. But yeah, good question. Any other questions? Yes.
Can you guys talk about
manually making
like a dot foo instead, so you
Yeah, so let's type ls right here, ls-a. Let's just see what all is here, and let's try something like touch dot foo, like this. If I type ls, we can see that the dot foo file is not being displayed, but it still exists. If we did the ls-a, we can see the dot foo file like this. One of the things that is often weird and takes some getting used to for people not coming from a Unix background, is that like file names have absolutely no semantic value to them, that the file name is just a string of text. And so if you want to create a file with a dot in front of it, you just put a dot in front of it. There's nothing special that you have to do. If we were doing something like touch foo.doc, like this is not a Microsoft Word document, even though it ends in .doc. That the meaning, the file name itself has no semantic meaning whatsoever. It only exists for human consumption. We will see more weirdish things about this in the future. Yeah, in order to, if you ever want to create a hidden file, you just put a dot in front of the file name and there's nothing special that you have to do. Did that answer your question? Or cool. Any other questions? Okay, problem number 3. So first 4 lines, again, the same, cd arm-rf quiz, maker quiz, cd quiz. There we go. And now these 4 echo statements right here. We'll do echo print hello space world like this, double arrow foo.py. When you have the double arrow and there's no file that already exists, Bash will create that file for you. If I type ls right now, we still have the foo.py in there, and it's just like it's concatenating to the empty file, to an empty string. So if we did run cat foo.py to see what the contents is, again, this is an idempotent command, so it doesn't affect the output. It's safe to do all the time. Just inspecting the contents of this file, we can see that it contains what we printed up here. The key thing about this problem here is that you just have to be careful about the type of quotation mark that you're using. So in Python, there is no difference at all between double quotes and single quotes. And so in the shell, if we're using double quotes, in Python, it's easiest to use single quotes just to differentiate that. But if in the shell, we're using single quotes, in Python, double quotes. So let me do this next line right here. We've done this first echo. We're on to the second one, which is the same, just going into a different file. Echo print hola mundo double arrow bar.py like this. And then this third one is using a single quote in the shell and double quote inside of Python. Echo print hola otra vez into bar.py. And again, this is using the single greater than sign down here instead of the double. So this is going to delete all the contents that we created right here and then just put it into bar.py. Hit enter. And then this last one is, I guess, the most confusing. If for whatever reason we have to use double quotes inside of the shell and have to use double quotes in the string inside of the shell, then we have to escape those double quotes. The backslash here is the escape character telling us that this is going to be an actual string literal or quotation mark literal that is being added, that should be passed over to the echo command. And so when I do that, echo print backslash quotation mark, hello again, backslash quotation mark, like that, into foo.py. Before actually running the Python, I'm just gonna cat foo.py, and we'll see that this backslash quotation mark here got converted into just a regular quotation mark right here because the shell interpreted that before passing it over to echo, passing just a quotation mark to echo. So this now is valid Python code down here, and we can run it, python3 foo.py like that, and we just get hello world. If that is your answer, then you get full credit. If that is not your answer, you have other things or you're missing that, then you get 0. Any questions on this problem? Yes. If you have quotation marks in it, then it's a 0, yes. It has to be no quotation marks. One of the things that we're going to be going over today is writing your own what's called shell scripts, which are using these, basically creating a file that's going to run these shell commands for you over and over again. And the shell in Unix is its full-fledged programming language, has lots of capabilities, and we will see that there will be some subtle differences between the quotation marks in the shell, even though there are no differences in Python. Last problem down here, I think the hardest because it's involving Git. Let's go ahead and reset our environment arm-rf quiz, make dir quiz, and cd quiz like this. Real quick side note down here, I use tab completion to type out this quiz right here. Tab completion puts a slash at the end of directories just so that you know it's a directory. There is no difference between quiz and quiz slash. Anytime where you you're typing in a folder or a directory, whether you put the slash or not at the end has no semantic meaning and won't affect anything. So this right here is exactly the same as what I have written in the actual quiz right there. Now here's the commands that we're running. So starting with git init, again, what git init does, besides all this output, is that it creates this .git folder for you inside of the folder that you're currently in. And by definition, that makes this a Git repository. We'll run these two echo commands up here, creating some Python code for us. Hello world into foo.py. So that's the first echo command. Now the next one, print hola mundo into bar.py. And if I run ls again, we have these two files existing down here. We have them both down here. And I'm now going to tell Git about them, that I want to make a checkpoint inside of Git, make a commit inside of Git that contains both of these files. So it'll be git add foo.py and git add bar.py like this. And git, let's see, before I run the git commit command, another idempotent command that you can always run is the git status command. And here we see that both of these two files are listed in green in the staging area. That means that when we run the git commit command, it'll be both of these two files that will get added to the commit. So git commit -m first commit like that. We're on this line right here at this point. And so I'll scroll up there. Now the next command for us to run is this git branch foo. Git branch foo. By default, when you first run git init, the only branch that exists on your repo is the master branch, and everything that you do will be done on the master branch. When you run the git branch command, it'll create a new branch for us, but it won't change the branch. We can see that it doesn't change the branch because in the purple over here, we're still on master. It is the git checkout command right here that actually changes our branch. So git checkout foo, and now we have changed from the master branch to the foo branch. All the things that we're going to do now are going to create a new commit under the foo branch and not under master. So echo print hello again, double greater than foo.py, git add foo.py. So we're going to be registering that change here in a second. The next one up here, the next command, git add bar.py. If you haven't made any changes to the file that you're working with, that's okay. Git add just does nothing. So if I run git status right here, the only thing in green is this foo.py because that's the only file we've changed, and we've run git add to let Git know about it. So it'll be it is staged for commit is the way we say this. When it's in green down here, we say this file is staged for commit. And so I run the git commit -m, make it exact, second commit like this. And it's actually created the commit now with that change into the foo.py file from this right here. If I run cat foo.py like this, we can see that these are the contents of the foo.py file. But now when I go git checkout master like this, rerun the cat foo.py, we go back to what the foo.py file looked like before we ran the all this stuff in the foo branch over here. We traveled back in time to our first commit over here. So we just ran the git checkout master, only two commands left for us to do. This echo command right here, echo print hola otra vez into bar.py. This is going into the bar.py file, not the foo.py file. So it's actually not going to have any effect on our final command down here, Python 3 foo.py, only running the foo.py file. We see right here what the contents of the foo.py file is. So when I hit enter, it'll run that and give us just hello world by itself. Again, if you have those two words, then full credit. Otherwise, anything else is 0 out of 1. Yes, there you go.
What would have happened if you had commit your original file before switching to or creating a new branch for?
Great question. So one of the things that happened on the practice quizzes is if I create a new file, something like we'll do echo test. We'll just create this into a file test like this. Run git status. And so we have this file test right here that that Git doesn't know about. It's not tracking this file. Is the verb that we say. Git is not tracking this file right here. Git is tracking this bar.py file up here. And so if I run git checkout, let's try going back to foo like this. Both of those files get, they don't change at all, and they remain as untracked files right here. I can go back to git checkout master and git status. Both of those files remain exactly how they are. If I run cat test, get cat bar.py like this, git checkout foo, cat test, cat bar.py. Nothing is changing about those files when I run this checkout command. If now, however, I'm currently inside of the foo branch. If I'm currently inside of the foo branch and I run something like git add test like this and git commit -m, this part doesn't matter, but we'll make it informative, added test like this. Now when I run git status, the test file down here is being tracked by Git. And so because it is being tracked by Git, as soon as I change my the commit that I'm looking at, Git is going to modify that test file to what it was at the previous whatever commit I'm looking for. So if I go back to git checkout master at this point and run ls, we see that the test file does not exist down here. And that's because even though the file existed on our hard drive at some point while we were working with master, we never told Git about that. So when we went back in time, Git only goes back in time to the things that it knows about. And so since it didn't know about the test file, it doesn't bring that test file back. Yeah. Okay, that's okay. So these weird things, edge cases about Git, are things that just take a lot of getting used to. And at first it seems maybe weird about why is this the behavior that Git is choosing to do in all these edge cases. As you use Git more, you'll see that this sort of behavior really is the only behavior that could make sense for these situations. And so in some sense, Git is doing the simplest thing possible, but it definitely takes some getting used to figure out or to have a sense of why these are the simplest things that can be done and why it's the right thing to be done. For the pre-lab work for this week, one of the things that I definitely recommend you all do is go back and rework through the Git tutorial from last lab. That if you feel like you're not 100% comfortable with Git, that tutorial does go through all of these sorts of edge cases inside of it. And what I found is when students go through it the second time, once you sort of have a little bit bigger picture of what's going on, you can catch those edge cases a lot better. A good question. Any other? Yes.
Why is it that when you do the last git checkout master and you do git, it shows both of the things when the first one is like branch before you do git checkout?
The question is between this line right here and this line right
Yeah,
here.
so like when you first get add food you get branch that isn't that on the master branch?
All these three lines, everything up to this point, yes, is happening on the master branch.
And then once you get checkout food, that goes on the food branch.
Correct.
But then before the last git checkout master add food.py, why does that show both the master and food if you have food branch?
This is a good question. So every time you run a git commit command, it contains not only the things that you've done since your previous commit, but also all of the previous things. So we previously modified foo up here and had this right here. So this is going to have both of those changes inside of it. Yeah, I guess the short answer is that checkouts always or commits always contain all of the previous information as well. The long answer is if anybody still has that question after this, we can talk about it after class and go into more detail. But the long answer is a very long answer. But it's a good question. Any other questions about the quiz?
You chose to commit underscores.
So yeah, these things here, another side note, the underscore looking things, it's common when printing out computer code sometimes to, it's technically not an underscore here. This is just a special font for the space character, just to let you know that there is a space character right here. Whether you drew something like that, added that in your output or didn't add it in your output, doesn't matter. You still full credit either way.
And then in the future.
Yeah, and
So then what is the underscore then just that little.
and then an underscore, yeah. So you know this is not an underscore because it's has the little thing sticking up. It's like a little cup. An underscore looks different, yeah. Okay, total up your score and pass the quizzes up to me.
How do you get that symbol? So what's the some kind of code for that?
It's literally just the space character with a special font. There's no special like code or anything. It's just the font that does that.
Some programmer font.
Yep.
Cool.
Are there any other quizzes that I should get? Okay. The main purpose of today's class, we're going to be starting to go over something called MapReduce. And this is a technique for large scale sort of parallel programming. And you're going to be using this to analyze the big Twitter data set that we were talking, I don't know, I've mentioned a little bit, every tweet since 2017. So trillions of tweets that you'll be analyzing here. And in order to do this, we're going to be using this shell scripting stuff in order for you to make your MapReduce system. There is a homework listed up here. The homework for this topic is a little bit different structure than the other ones. There's going to be a lot of computation needed for this one. So the due date is going to be like 3 weeks from now. You'll have plenty of time to work on it. And today in class, we probably won't fully finish the material that you need for it. We'll probably have to clean up a little bit of stuff on Monday next week for that. But you'll have lots of time to work on this homework. And I guess, main takeaway is that there is no homework due for this weekend. No homework due next Tuesday. Another quick announcement is that coming down here to the lab, Friday's class, I have to cancel for us because of the data science program is having a thing that I have to be at. And so there's not going to be a lab, in-class lab session. There will still be a little bit of lab work based on the stuff that we'll do. But if for whatever reason you can't finish it, no late penalty on this lab. And or I'll extend the ability of collaboration to just collaborate with people however you would like on the lab so that it's, yeah, I apologize that I'm not going to be available. Again, one of the main reasons for having these Friday classes is so that we'll have enough class sessions to cover all the material with my paternity leave at the end of the semester. And so we'll still have plenty of class sessions with this Friday canceled in order to be able to do that. So shouldn't be long-term a big deal. Question? I haven't decided, but at least 3 weeks. So long time. Good question. Any other administrative questions before we get into technical material stuff? Yes. So yes, 2 weeks from now, we will have, there will be other homeworks due before this homework right here is due. The actual programming that goes along with this homework shouldn't be very long, maybe like, I don't know, 2 or 3 hours, but it might take you a long time computationally to have it run. So that's why I'll be giving you a long time to work on this assignment. So yeah, besides the quiz for today handout, there's this other shell scripting quiz. This next Wednesday's quiz will come from the material on this handout right here. And so I definitely recommend having this out, taking notes as we go through things today. If you want an electronic version for whatever reason, under our topic right here, quizpractice.pdf, that's where the electronic version of the quiz is. I'm going to do some high level talking about the shell first here, and then we'll get into the actual technical stuff about this quiz. And again, the technical stuff here is what you'll need eventually to complete this MapReduce stuff. So first, real quick, definitions. I've been sort of using the terms terminal and shell interchangeably so far in this class, but they're not exactly interchangeable. The terminal is the thing that you're actually interacting with right here. My computer happens to have 2 terminals installed. Xterm is this one up here. Down here is called GNOME terminal. And you all are using different terminals than I am. Based on whatever system that you have. The terminal is just like the visual thing that you interact with that actually interacts with your own operating system here and like this own window environment. The shell is a non-graphical program that actually runs the commands. And after you've logged into the Lambda server, all of you are using the same shell, even though you're using a different terminal. And the shell that, there's lots of different types of shell programs. I want to just do a real quick history of them because there's, I don't know, some fun anecdotes here, and then we'll get into the technical parts. So the first shell created by this guy, Ken Thompson, is called the Thompson shell, made in 1971, and it's often just SH for short. SH was inspired by this thing called runcom. If you've seen all in your dot files and like the previous lab, there's a lot of these files that end in RC. That RC stands for runcom, which is something that existed before Unix. And so like this dot vimrc dot bash rc, that RC stands for runcom. And nowadays, anything that is like a configuration file for something is just traditionally ending in RC right here. Because that's what runcom made its configuration files end in. Since Ken Thompson wrote his original Unix shell, there's been a lot of replacements. One of the important ones is called the Bourne shell from 1979. And this is what Unix, so Unix is a proprietary thing coming out of Bell Labs. Unix, since 1979, shipped with the Bourne shell as its default programming environment. The Bourne shell and the Thompson shell have slightly different features that you can use in the command line. And all of the different shells that people have created since then all have slightly different features as well. So important open source shells, the Alchemist shell, called that because of written by Kenneth Alchemist, also known as Ash is the name of the shell. written in 1980. And then the one that's the most famous of all, the Born Again shell Bash, 1989. The reason it's called the Born Again shell is because, so it's based off of Stephen Bourne's shell up here, but this one up here is proprietary. This one down here is open source. And in particular, it's GPL licensed, which has this sort of quasi-religious movement behind it. And so the Born Again shell is specifically like intended to remind you of being born again as like a born again Christian, but you're a born again Linux user if you're using the Born Again shell. There's been a big, so the reason this was written is because there's been a big divide between BSD and GPL people for the past, since the 1980s. And if you don't know who Richard Stallman is, he would like to remind you that we're not running Linux on the Lambda server, we're running the GNU/Linux. Because all of these systems that, all the command line programs available on the Lambda server are part of the GNU project. If you're running a Mac, then you're not, you're still using a Unix system or a Unix-based system, but yours is based on BSD, and so there's some slight differences there. We're going to be exploring some of the differences between the Bash shell and the Dash shell over the coming week or so. And the Dash shell is called Dash because it's specifically designed to be fast. And so all the system scripts and scripts that you write in this class will be written for the Dash shell instead of the Bash shell. Last, I guess, important shell is ZSH. If you're on a Mac, this is your default shell, ZSH. So slightly different than Bash, but mostly the same. The reason that all of these things are mostly the same is because they're what are called POSIX compliant shells. POSIX stands for the Portable Operating System Interface, and they added an X so that it sounded cool. And I think that is the official explanation. POSI did not sound cool, so they added it as POSIX. All of our shells are, all these things have slightly different behaviors, but POSIX is the standard that if you're writing things that are going to be cross-compatible between systems, you'll want them to be POSIX compliant. And one of the reasons the Dash shell is very fast is because it has a minimal set of features in order to be POSIX compliant. Bash has a whole bunch of extra features, which make it quite a bit slower than Dash. Doesn't matter for like interactive use, but matters for shell programming. POSIX, so again, invented in like the 70s. And so back at the time, it was the most user-friendly thing around. But we're going to see that in order to maintain backwards compatibility for like the past 40 years or so, there's a lot of like really weird edge cases here. And so all of you at some point over the next couple of weeks will have this expression. I certainly have this expression as we're working in the shell environment. And so your quiz is going to scratch the surface of some of these edge cases this week. There are non-POSIX compliant shells. There are some, I don't know, some people like to use these. The most famous, the fish shell and the oil shell. My sense is that these are never going to take off, and it's going to be like Bash and Dash are the main shells that people are using for the coming at least coming couple decades. These have both been around again since the 70s, and so or Bash has been around since the 70s. This is 1997, but POSIX compliance has been around since the 70s, and it's not going away anywhere. People are still using this all over the place, and so that's what we'll be using. I don't know, any high-level questions? We'll get into technical stuff next. That is our history lesson over. Okay, so for these problems, again, the first four lines of all these problems are going to be the same for everything, just setting up our quiz environment to be in like a standard environment. And then the subsequent lines will be different for everything. To make things a little bit easier to refer to, I've added numbers to the left of everything over here. The $ is still the prompt. I didn't have the numbers on the first ones just to try to reduce confusion, but I think it'll help going forward so that we can talk about easily talk about reference individual line numbers. For this quiz, I'm not going to like type any of these quiz problems exactly into the terminal while we're going over it. I'm just going to go over the concepts at a high level and leave these quiz problems as things for you to be able to practice on yourself. But we'll be going over all of these concepts in the terminal. So the first of these concepts is the pipe. And the pipe is on line 8 down here, this vertical bar. That vertical bar is what we refer to as the pipe. On a US keyboard, it is above the backslash, above the enter key. So sort of in the top right corner of a US keyboard. Come back over to the terminal environment over here. I'm gonna reset our screen over here, and then we'll take a look at what this pipe command can do. One of the common very common commands to combine together with the pipe command right here is this grep command. And so before we talk about the pipe, we'll just talk about exactly what the grep command does. And in order to talk about the grep command, let's remind ourselves what the cat command does. So cat by itself takes whatever I type in on standard in and outputs it to standard out. By default, standard in is what you're just typing in here. So if I type hello world like this, then cat will output that to standard out. There's hello world, hola mundo. And if you're in this, so the cat program is currently running. We're in the cat environment. You can press either Control C or Control D to get out of the cat program. If you're on a Mac, that's Control and not Apple C, Apple D, not Command C, Command D, but Control C. Again, with something like output redirection, do that into test. And now whatever I type in here, hello world, hola mundo, put into this test file instead of being output to the screen. I press Control C right now, and I can view the contents of this file, get my input from this file by saying cat test instead of just cat by itself. And there's the contents of that file. What's different about the grep command is that grep does not output all of the lines to standard out. It filters before doing outputting. It filters according to a regular expression that you type in right here. I'm going to put the regular expression in quotation marks, and we'll just use the letter H like that, as this is my regular expression that I'm searching for. There's a very simple regular expression. Any line that contains the word H or contains the letter H will match this regular expression and get printed to the screen. So if I type hello world like this, that gets printed to the screen because it has a letter H inside of it. If we go Latin and go salve mundi like this, this does not contain an H inside of it anywhere. And so when I hit enter, you see that that does not get printed to the output, to standard out. So I'll press Control C. Well, let's see. Let's just do a couple more examples. This, just mashing my keyboard right here, no H in here. There is an H right there. There is an H in this line right here. So when I press enter, that will get printed to standard out. This is case sensitive. So if I do like a capital H like that, that does not get printed to standard out. If I do a lowercase h like that, that will get printed to standard out. Do Control C like that to end it. And just to do another example of this grep program, I'm going to open up Vim, open up that test file. And so we have two lines right here that contain this H inside of it. Let's go ahead and add this salve mundo like this. And this is going to be basically exactly what is the first problem on the practice problems. If I do cat test like this, then that's going to output all of these lines. With grep, or what the pipe does is it takes the output of the output of the command to the left, and it makes that be the input to the command on the right. So cat test grep the letter H like this and hit enter. The output of cat test was these three lines right here. And again, the grep H filters these three lines, only keeping lines that contain the letter H. And so it's only keeping these two lines right here, not keeping this last line. And so it filters out, removes this last line for us. Very common when we have large outputs from things to just pipe those to grep in order to get like the things that we're actually interested in. Any questions so far? Yes.
So grep filters line by line.
Great question. Question is, does grep work on a line-by-line basis or a word-by-word basis? And the answer is a line-by-line basis. Every one of these Unix programs that we're going to be talking about is going to be working on a line-by-line basis about things. And that's just sort of like one of the principles about how Unix works, is that like the fundamental unit of meaning or information is always going to be contained on a single line somehow. So yeah, grep filters on a line-by-line basis, and every other program that we work with will also be on a line-by-line basis. Great question. Any other questions so far? How many people here have, raise your hand if you've used like grep before at all? A couple people, sort of, okay. Yeah, we'll be doing lots of interesting things with this grep command. Let's see. So another useful command is the WC command. WC stands for word count. And if you just type WC like this, it gets its input from standard in again. So whatever is being typed in. So let's do hello world, hola mundo, like this. And let's go add our Latin at the end, Control D. And then at the end, it gives me an output of how many lines there were, how many words there were, and how many characters there were. You'll notice that there's no explanation of this output. It's not saying like lines 3, words 6, characters 35. It's a very common feature of Unix commands, is that they are not verbose. They do not provide any extra information than like the literal things that they calculate. And that turns out to be actually very useful when you're combining commands together, but it also makes it harder to learn about like what commands, what they actually do. And anytime there's a command that you want to know more information about, the standard reference for where to look about a command is called the man page. And if you type man WC, man, and then the name of the command that you want to look for, then it will tell you all the information about it, giving you all the possible things that you could pass to it and some example uses. Man is short for manual. Again, for historic reasons, Unix programmers typically only use the first syllable of things. Yeah, the mnemonic to remember this is, if you want the manual for the command, it's man and then the name of the command. In practice, people, you can just Google like WC and it will show you the man page is usually the first thing to come up. Again, we're using the GNU system. The Lambda server uses GNU. Your machines, if you're on a Mac uses BSD, and there will be some subtle differences between the BSD and the GNU versions of things. And so if you are looking on Google, you might accidentally hit the BSD page instead of the GNU page. For our purposes, most of the time with WC, we're only going to be interested in the very first number over here, how many lines there are. And if you do WC-L, L will give us the number of lines. And so now do hello world, hola mundo, salve mundi, like this, Control D, and it just prints out 3 down here as the number of lines. We have already, so this is the thing that I typed into the WC input right here. But we already have a file. We already have this test file that contains that information, cat test. So if I wanted to find out how many lines are in this particular file right here, the easiest way to do that is cat the file, pipe that to WC-L. Take the output of this, the output of running cat test, this stuff right here, and make that be the input to WC-L. We saw that I manually typed this in as the input right here, and we got the answer 3. We don't like doing things manually, though. We like automating that. So the pipe right here automates that for us and just tells us the number 3 right there. This is useful. So yeah, lots of well, one more example before we get into a cool use case of this. the pipe can be chained together as many times as you want. So here, we're just using it on the test file. We've seen how we can filter the test file like this by running the grep command on it to filter. If we want to know how many things match this regular expression, how many lines match this regular expression, or in this case, how many lines contain the letter H, then we just combine, we first run this, the output of this will make that the input to wc-l, and we'll do that by putting a pipe between those commands. Pipe wc-l like that, and it tells us there are 2 lines in this file that match this regular expression right here. The sort of mnemonic to keep in mind about like what the pipe does is that it's called the pipe because it's connecting, it's like a physical literal pipe that connects these 2 things together. Any questions so far? Okay, we're going to take a look now for a second at that Twitter data set and see what are some like cool, interesting things that we can do with just these commands right here with that Twitter data set. I'm on the Lambda server right now. The Twitter data set is located so in the /data/Twitter dataset folder. I'll hit enter like this. And so I did the ls command. So you can see there's a whole bunch of zip files inside of this folder. I'm going to cd into this folder here. We'll type ls, we get the same output. And the format of these zip files, so it's just contains the date inside the name of the zip file, and each zip file corresponds to all the tweets sent for a particular day. And so you can see this is, I believe, yesterday right here that we have the information up to right now. I'm going to load a zip file in Vim. You can just use Vim and then the name of a file, and whether it's an ordinary text file or a fancy file like a zip file, Vim is able to load that for us. So I'll do that. And now each one of the lines that it's displaying right here is one of the files that's contained inside of the zip file. There are 24 files here, 1 for each hour of the day, and each one of these subfiles contains all of the information about all the tweets from that particular hour of the day. In order to open one of these files, you can just move your cursor above the file and press enter. So we'll start with that. It'll take a second here because it has to actually uncompress all of that information now and display it to the screen. And so this is the contents of that actual file now. Each line of this file is an individual tweet. Again, anytime you're on a Unix system, you should think of lines as being like the fundamental unit of data, like one data point is one line. And so each one of these lines corresponds to one data point. And if I'm going to use my Vim knowledge to know that if I press the uppercase letter G, Shift G, it'll take me to the end of the line. And so we can see here that there's 135,000 tweets that are contained in this this file, or yeah, sent this hour of this day. Yeah, I think I might have misspoke earlier. This isn't actually all the tweets. This is all of what are called geolocated tweets. So tweets that contain GPS coordinates associated with them, which is 2% of all tweets that are sent. So there's 50 times this number of tweets actually sent yesterday at 1 a.m. Let's go ahead and :q will leave that for us. And then :q again to leave the zip file. And what we want to do is we're going to write a short bash command right here, a short shell command that's going to count all of the number of tweets that are contained in one of these files. In order to do that, the first thing that we have to do is we have to figure out how can we output the contents of one of these files to the screen. There's a command called unzip, which basically works like the cat program, but it takes a zip file as input and outputs the zip file to the screen. -c means that it's going to decompress the file for us and put it to standard output. And then I'll put the name of the file here, like that. And I'm going to hit enter here in a second, and it's going to fill up our screen with a whole bunch of tweets. So you can still see this JSON information for all these tweets being sent out to the screen. Now, if I want to know like how many tweets are actually contained in this zip file, I can do pipe wc-l. And again, it'll take I don't think it takes about 30 seconds or so in order to do this, as it unzips the file and loops through every line in the file, counting how many lines there are. We'll see that, yeah, I mean, all the sort of bash shell stuff that we're gonna get to, relatively unintuitive compared to Python programming or other languages you might be used to, but extremely, extremely powerful. That this is just like a one-line command that's, once you're used to these sort of things, is doesn't take any thought to type out. You just type it out, and you can instantly do what would probably be like at least 20 or 30 lines of Python, and not hard Python, but complicated enough that I'd have to think about it. This I'm not going to have to think about. While this is running, it's actually probably taking a little bit longer, probably because some of you are probably running the same command at the same time, which is totally fine. But I'll make a comment that this data set is stored on a what are called HDDs, sometimes referred to as like spinning Rust hard drives. And they slow down considerably when multiple people are accessing the information in parallel. And that's going to be one of the main causes of the Twitter data set homework assignment, this MapReduce homework assignment to analyze all these things, one of the main causes of the slowdowns. Okay, so there we go, it finished, and we can see that there are a total of 3.4 million tweets here sent with GPS coordinates sent yesterday. If I wanted to be a little bit fancier, I'm not gonna, took a little while to run, so I'm not gonna actually run this, but I can use a regular expression to filter out those tweets and say, coronavirus, type that. Again, it's in my terminal window, it's going on into multiple lines, but in the shell, the underlying thing, it's not on multiple lines. And so I'll hit enter here. I'm not going to let it run, but this would filter out all of the tweets that match this particular expression right here. And so we could find out how many people are talking about coronavirus yesterday on Twitter. I'll just go Control-C so that we stop that. And one of the things that your lab is going to ask you to do is to write a couple of variations on this command right here to do just some quick data analysis of these Twitter files. But this will be the like your starting point for what to work with. Any questions so far? Okay. So one of the weird things about this that's going to cause a lot of problems throughout the semester, and I'm doing that intentionally because they are illustrative problems, informative problems, is that this folder contains a space in the name of this folder. And so if I type pwd again, this is the current working directory that I'm in. Let's do a real quick, well, yeah, I won't run ls, but we talked before about there are these special files, dot and dot dot. Dot always refers to the current folder that you're currently in. So if I do cd dot, that never changes your path, but cd dot dot will take you up one folder, take you to the parent folder. And so now I'm in the data folder, pwd, I'm in /data instead of data/Twitter datasets. And if I want to go back into this Twitter dataset folder, I can't do cd Twitter space dataset like this, because the cd command here is not going to know that this is just like one argument, and it's going to interpret this space as this being the first argument and this being the second argument. If I hit enter, you see the cd command says too many arguments. Cd can only have one thing passed to it. So there's a number of possible solutions to this. One is you can escape this space, add a backslash right here. You might have noticed a backslash in the previous command that I ran a long time ago. That was specifically so that this space here was this whole thing interpreted as a single argument. A simpler, what most people find simpler thing to do is to put it all in quotation marks like this, either single or double quotation marks. And now this will actually be interpreted as a single argument. And you can do that. No difference at all between this and this. So this is going to come up on your, I'm just going to go back to our home folder now. Easy way to go back to your home folder, CD by itself, and we'll go back into the quiz folder like that. This is going to come up on your quiz in terms of the next section of the quiz, which is variables, section 2. In variables interact with spaces in very confusing ways. So we'll probably start talking about this right now and probably won't get a chance to finish this. But at this point, you've seen everything that you need to know for completing the lab. And on Monday, we'll finish up whatever about the quiz that we don't get to today. Variables in Bash, you create them by saying whatever the name of your variable is, then it equals, and then whatever the value of the variable is, like this. And it's important that there are no spaces on either side of the equal sign. No spaces on either side of equals. You'll get weird, confusing things happening if you put a space. The way you access variables, so if I do something like echo recall prints to the screen, if I do echo var, it's going to just interpret this as the literal string var. If I actually want to access the variable, you have to use a $sign, put a $sign in front of the name of your variable. And now Bash will interpret this as saying, okay, I know this is a variable. Let's come back up and substitute whatever the value was, plug that in right here, and then pass that value over to the echo command. So do that, and we get value out there like this. If I come back up here and add quotation marks around var equals value like this, echo $var, you'll see that these quotation marks don't appear. Anytime in the shell, any POSIX compliant shell, you see quotation marks, these quotation marks are going to get interpreted by the shell exactly at that location. And so it's just going to say that this and this are exactly the same as each other. In general, anything that you can write with quotation marks, it's possible to write it without quotation marks, and the shell will not complain at all. So that brings us to the issue of spaces and how those are going to be tricky. If I type, before I do this, I'm just going to delete everything in this folder. We'll do it using things that we've already seen, arm.href, make dir, quiz, cd quiz, ls, nothing in here. I'm going to create a variable var equals, and we'll use quotation marks right here. This is a test like that. So there's 4 words inside of this separated by spaces. Echo $var, that's totally okay. Creates, outputs exactly what you'd expect. But now I'm going to use the touch command, touch $var like this. And what's going to happen? What's going to happen is a little bit unintuitive here. So anytime you have variables and spaces, that's like a sign that like you really need to start paying attention. Variables and spaces interacting, you really need to pay attention about what's going to happen. I'm going to hit enter right now, and I'll type ls, and we'll see that there's actually 4 different files were created. A is test and this, 4 different files. What happened here is that this variable does in fact contain the string, this is a test, and it is just 1 string. But when we do this substitution here, it literally just copies and pastes this right here, and then interprets this whole thing as a normal shell command. So this line right here is exactly the same as if I did touch, this is a test, like that. Exactly the same thing right here. When you use touch with multiple different files, multiple arguments, it creates 1 file for each of those arguments. If I only wanted to create exactly 1 file that was called this is a test, I would have to put quotation marks around that whole thing. Touch this is a test like this. And now when I run ls, do ls-l, ls-l, there we go. We have those original 4 files and then 1 file right here that contains all 4 of those things together. If I do touch, let's go ahead. rm star is going to delete all of these files. We'll talk about what the star does next time. If I do touch inside of quotation marks, $var like this. Inside of single quotation marks, the $, the variables will not be expanded. Hit that, hit enter. We get the variable, the only file name is called literally $var. If we put it inside of double quotation marks, the variables will be expanded and substituted inside, and then it will be treated as a single parameter to the touch command. I hit enter, type ls, and it's a single parameter to the touch command. So the takeaway is double quotation marks does the expansion and is a single parameter to the command. Single quotation marks, no variable expansion and is a single parameter to the command. No quotation marks does the expansion and is multiple parameters to the command. We'll review all that on Monday and talk about some of the weird implications of that again, finish up the quiz material. That's it for today in class. If anybody has any questions about anything, I'll stick around, get those questions answered. Otherwise, I'll see you all on Monday and hope you all have a great week.